Hello, today I want to talk about exact differential equations or solving differential equations by exactness. I guess called both of those things. Before we talk about the technique, I just want to define two forms of differential equations. So there is what we call normal form of a differential equation. And I should specify here, we're looking at first order differential equations, right? Just where we have only one derivative, right? Not a second derivative, third derivative, etc. No higher derivatives. So normal form means, well, kind of the normal way you would maybe want to represent a differential equation. Derivative equals some messy pile of x's and y's, right? That's called normal form. But there are other ways that you could write differential equations. You don't have to necessarily have it strictly in that form. You could do what's called differential form. This is where you could imagine doing a little bit of algebra on the normal form, multiply over the dx, maybe subtract the resulting expression off to the other side, and you could get it in something that looks like this. Some function times dx plus some function times dy equals 0, right? So this is called differential form instead of normal form, right? For example, say you had the differential equation in normal form, consider the dE, which I'll write. I'll write one in normal form, and then I'll show how we can take it and rewrite it in differential form. So suppose you had this differential equation, dy dx equals, let's say we had negative 2y divided by x plus 1, right? Say that we had this differential equation in normal form. So this is how I have, sort of the green version up here, right? This would be the normal form version of this dE. Let's convert to differential form. So here, probably the easiest thing to do is just cross multiply. So you'd get x plus 1 dy equals negative 2y dx, and then add that 2y dx to both sides. And this would convert this into differential form, right? So now this we would call the differential form. Same differential equation, just written in a different way. So this is something that you might ask now, why would this be written? Why would that be called differential form, right? One reason for that is and if you haven't had maybe Calc 3, don't worry too much about this reference. I'm just explaining the name more than anything else. It's not something you'll need to solve this. But if you have the total differential of a surface, right? Sometimes this is an idea that's discussed in Calc 3. So if you have a surface f x y, right? This, how would you write this? This is, you would call it df would be the partial derivative of f with respect to x times the change in x plus the partial derivative with respect to y times dy. This is called the total differential of the surface. So that's why this is called differential form, because the left-hand side kind of looks like a total differential, right? It looks like some function times dx plus some function times dy. So the left-hand side could look like a total differential of the surface. So this definition, and again, don't worry if you haven't had Calc 3, but I'm just explaining the name here, right? But this definition does, in fact, motivate a method of solving this kind of differential equation. So here's what you can do. So there is, so here's another definition, right? This is what an exact differential equation is. So if there exists a function of two variables, right? Which in Calc 3 we tend to call a surface, right? But here you could just say it's a function of two variables, big F of x, y, right? Such that partial derivative of f with respect to x equals p of x, y, and the partial derivative of f with respect to y equals q of x, y, right? Then we say the differential equation p of xy dx plus q of xy dy equals 0 is exact. So that's this notion of exactness, right, is saying that if these coefficients on the dx and the dy came about how as the partial derivative of some surface, right, of some function f, that just like a total differential would have, right, then we call the resulting differential equation exact. So that's the definition of exactness. Right, if there does exist some surface, then we get to call the dE exact. You can do a little test for exactness. This is a nice little result. So a test for exactness, you could say if the derivative of p with respect to y equals the derivative of q with respect to x, then we say that, sorry, not even we say, this is more of a, not a definition, this is a test.
May I have your attention, please? This is campus security. The campus will be closing in 15 minutes. Please start to gather your belongings and head towards the exit at this time. Thank you.
This video will not last more than 15 minutes. I promise you will have no further to watch than that. So if dp dy equals dq dx, then what do we have? Then it turns out the differential equation in normal form, right? P of xy dx plus q of xy dy equals 0 is exact. Right, so this definition up here where we're saying there exists some surface that we could use to right, whose differential represents that left-hand side, this is a way that you can test to see if there exists such a surface. And it's in fact, if and only if, right, it goes both ways, this test. Why is this the case? Well, this is essentially a consequence of Clairaut's theorem, right? That mixed partials are equal. If you do derivative with respect to x then y or y then x, you get the same thing. Right? This is just actually a slight restatement of that. Because if you look here, right, what do I want P to be? I want P to be partial x of f. So this quantity is partial x then partial y of f, right? That's what this is when you plug it in. This quantity is the partial with respect to y of the partial with respect to x of f. Versus this quantity is what? This is the derivative of q with respect to x. And I want q to be partial f with respect to y. So this is going to be the partial x of the partial of the y partial of f, right? By Clairaut's theorem, those have to be equal. The mixed partials in each order, those have to be the same. Right. So that's where this test for exactness comes from. Right. Now, here is the strange thing. Sometimes, so note, sometimes an equation, sometimes a dE is not exact, but can be made exact multiplying both sides by something, by some function. Right, by multiplying the dE by some factor. Right. This is kind of strange property of exactness, right? Because say, if you say, hey, is this dE separable? Well, if you multiply both sides of it by anything, you can't change it from being separable to non-separable, right? Or if you say, is this differential equation linear? Well, you can't change whether or not it's linear by multiplying both sides by something. So that's where exactness is actually a little bit strange, because sometimes you can change it from exact to not exact, or from not exact to exact by just multiplying by something. let me show an example of this. So if you look at actually exactly the differential equation we had up here, this 2y dx plus x plus 1 dy equals 0, right? If you look at this differential equation, right, this dE is not exact, right? This is not exact because if I take the y partial of p, right, I get 2, and that is not equal to right, that does not equal the x partial of q, which is 1, right? So this fails the test for exactness. But multiply both sides by x plus 1. Where did I get that from? I'm not telling you. Rabbit out of a hat, Oracle at Delphi, something gave us this idea, right? And I'm going to multiply both sides by x plus 1. So now the equation becomes 2y x plus 1 dx plus x plus 1 squared dy equals 0, right? I claim that this new equation is actually exact. This is what I'm saying. It's kind of strange. Test it, right? Let's do the test. So now take the partial derivative with respect to y of that first expression, 2y x plus 1. It gives us 2x plus 1. This does equal the partial derivative with respect to x of the second expression of q, which is also 2x plus 1, right? So it was not exact, but we made it exact after we multiplied by x plus 1, right? So here, once again, what's the consequence? Here, this was not exact, right? But then we took exactly that same equation and we multiplied both sides by x plus 1, and we ended up with this differential equation, and this is exact, right? Even though they're equivalent, right? One is exact and one is not. That's what's sort of strange about this technique. And I didn't say at all where I got this from, right? So, how would you think of that? That's difficult. There's a lot there. There's a lot to unpack. This is something that you'll see how, in at least some cases, how one might come up with such, oh, I should multiply by blah 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 in our Euler primary source project. Right? So this is there's a lot to unpack there. But here I'm just at the moment looking at the test for exactness, and then this idea that a differential equation could be made exact sometimes by multiplying both sides by some strategic expression. Right? All right, now here is a nice technique. It turns out that once a DE is exact, we can actually solve it rather quickly. We can solve it. Here's what you do. You just find f of x, once it's exact, such that these two equations are both true. You want df dx to equal p, and df dy, you want that to equal q, right? So just find f such that both of those conditions are true simultaneously. Right? So you want the same f to work for both of those equations, right? Then the solution to the DE is f of x, y equals c. It's just the level curves of that surface. You could think of that as taking the total differential of both sides of that equation, the c goes to 0, right? And you get back the original differential equation. So that in differential form. So that's our technique for solving an exact differential equation. Let me demonstrate this. It's a pretty clean technique. So let's demonstrate it on this equation, right? This was our equation that we said was exact, right? So let's solve this equation by exactness. So I have 2y x plus 1, there's p, right? And then I have x plus 1 squared, that's q. I'm going to solve this by exactness. So here's what I do is I want f of x, I want f of xy such that these two conditions are simultaneously satisfied. I want the x partial to equal p, and I also want the y partial to equal q, right? So what can I do? Well, here, take an antiderivative, right? Take an integral with respect to x. That'll give me a formula for f, right? So if I integrate this with respect to x, what's it gonna look like? Well, this, let's rewrite this a little bit just to make it a little more clear. This is 2xy plus 2y, right? So if I integrate this with respect to x, what do I get? I get x squared y plus 2xy. All right, that's the integral with respect to x. But then you also get plus, and I'm going to call it, say, c of y, because it was a partial derivative with respect to x. So there's a plus c when you do the antiderivative, but it could be any function of y, because the partial derivative treats y as a constant. Partial derivative with respect to x treats y as a constant. Now here, do an integral with respect to y, because this is a partial derivative with respect to y. So do that, and what do we get? We get, well, this whole thing was just a function of x, so I just get x plus 1 squared y plus maybe some constant of integration d, but that constant of integration d really could be any function of x at all, right? Okay, so what do I need to do now? Well, now I need to get one formula, f of x, that satisfies both, let's call it equation 1 and equation 2 at the same time, which at the moment doesn't look good. They don't look compatible, right? They don't look compatible at all, but they actually are. If I unpack this a little bit, this equation 2, right? If I do a little bit of algebra there, then I see that a strategic choice of C and D could actually make these match, right? Because if you look at what we have, this equation 1 and equation 2, they already agree on that term x squared y. They also already agree on this term 2xy, right? The only thing that's different is this term right here, this term y, right? Ah, okay. So what do I know? I know then that this c of y must be y, right? That c of y must be that y term. And then up here, I don't have in equation 1, I don't have any terms that just involve an x. So this d of x, this must just be 0, right? I don't need any x's at all. I don't need any terms that only involve x, right? That's what that d of x would represent. So now I have my surface, right? So my solution, the equation that solves both of those conditions at the same time is x squared plus y plus 2xy plus y, right? That satisfies both equation 1 and equation 2. There's the right partial x and the right partial y, right? So the solutions to the DE is this family of functions. It's x squared y plus 2xy plus y equals c. That's the solution. This sometimes is called an implicit solution. And sometimes when you do this, you're just kind of stuck there. you just stay there because there's not much you can do. Here, I can do a little bit of algebra and actually turn this into an explicit solution, right? If you solve for y, then that's an explicit solution. So I could I could say this is y times, you can factor out that y, right? And then I could say this is y equals c over, this is actually x plus 1 squared, right? So I could actually factor that, and now this is an explicit solution. Sometimes the algebra is too weird and that last step isn't possible, but you can still get an implicit solution at least. So there we go. We solved a differential equation by exactness, and than 15 minutes later from that intercom announcement. So great. Thanks so much.